Good afternoon, everybody. Wow, an in-person lecture. This feels really, really good, and I'm glad to see you all. Can everyone hear me okay? Okay, perfect. Can I be heard on the webinar? Excellent. So it's really great to have you all here. This is the 2021 Physics Departmental Welcome and First Tea, but because we're responsible adults, we're going to flag the tea. Nevertheless, some of you know who I am and others of you don't. So let me give you a quick introduction. I'm James Aniletis. I'm the chair of the physics department. I'm a condensed matter physicist by day, but I'm also from New Zealand, which is why you have this funny accent that you have to listen to. The other really important part of my life is, of course, I have a small family who live right here at Berkeley. So my wife and 3.5-year-old. One of those. Well, the last two things are kind of tied. Well, actually, all those three things are tied together in the way I met my wife, actually, which was when I told her what I did. I told her I was a condensed matter physicist. And because of my accent, she thought I said I'm a condensed metaphysicist. So I think that kind of got me the hook, but once I could learn to pronounce my R's correctly, I don't think it was, she still stuck around. But anyway, did anyone get metaphysicist? Never mind. Okay. All right. So last time I gave this talk, I started with a question. What is our mission as a physics department? And the reason why I was thinking about this question is because I'd just become chair and I was interested in what I had to achieve as chair, but also what we had to achieve as a community. And so I solicited some feedback from the community, and everyone came up with different kinds of ideas. From our mission is to include all in the pursuit of knowledge, to provide an internationally respected education, to create community of scholarship and leadership, to drive new technologies that can transform our economy, to push the boundaries of knowledge, educate the next generation of scientists and engineers, help understand the physical universe, help our society tackle existential problems. These are all things that we would see as a mission individually, but also perhaps as a mission as a department. Now, I didn't have a straight answer last time, and I still don't have a straight answer about exactly what our mission should look like, but we did nail down that our mission certainly orbits two things that we do every day here: research and teaching. And another way to frame these two things is really what they're designed to achieve. Understanding the world around us on the one hand, and helping others understand the world around us, bring them along in our quest for pushing the boundaries of knowledge. But on thinking about this, I thought that in many ways, this is really what is our mission as physicists, like what we would think of as our individual mission, what we want to achieve. And for each of us, that turns out to be rather different, and that's okay. In fact, that's exactly the kind of diversity of the intellectual diversity that we'd like to foster as a department. So that got me to thinking that the real mission of what we're supposed to do as a community is to create a community that facilitates how you realize your own mission as a physicist, what you want to do as a physicist, to help us each realize our own mission as physicists. So if we can do that, then I think we're doing all right. The question is, how do we create a community that achieves this? And that is basically what I see my job as, and also the way I see my connection to you all. We have three major tools in this effort to achieve this kind of community. We have our students and our postdocs, we have our faculty, and we have our staff. And it's with those forces combined that we can really achieve this kind of community. The only way we can do this is really if we have those three tools working together as one. And I'll try and give you a few examples of that as I go through my talk. Okay. It's been really hard to do that this last year and a half, for obvious reasons. We saw our hallways emptied a bit over a year and a half ago as we had to go online very suddenly. Then we trickled back. We started with our research community and a few of our staff. Many of us that are here today had to get tested every week to make sure that we weren't spreading the virus. And eventually, slowly but surely, we got some of our research programs back. This summer, we started bringing our staff back. And there has been its ups and downs that roughly follow this curve. And I tend to think that even with those ups and downs, we actually managed to achieve a lot as a community. And now suddenly, we're back in person. So our campus has gone from looking from the picture on the left to being completely full on the picture on the right. And that has been associated with its own anxieties. I'm sure every one of us here has felt some sense of anxiety about what it's like to be learning together again, what it's like to have our peers next to us, to be in a classroom full of other students, worried about our own health, but more so for many of us, worried about the health of those at home who are vulnerable or can't be vaccinated, or those who are older, for example. And all of those anxieties are real, and we're trying to do our best. But I have to say that speaking for myself, and I hope speaking for a great many of you here today, it feels great to see you all again. It feels great to see each other in the same place, because that is the center of what it is to be a community. That is the center of what it is to try and grow as a community. We need each other. So how did we achieve this? How did we maintain our community? Well, first of all, our staff really came through. So particularly our facilities director, Anthony Vighton, along with his team, Carlos and Bustamante and Eleanor Crump, really tried to make our corridors safe for us to return. Everything from making sure that surfaces were sanitized at the very beginning to now making sure that the air changes in every single lecture room or instructional space or what it should be to make us feel safe. Our instructional group had to develop new kinds of ways of teaching us, whether that was online tools or kits that would help us keep some measure of social distancing while still facilitating our educational mission. And they were critical to keeping the quality of our education extremely high while still maintaining a measure of safety. And then finally, our student services and support. We were critical in helping our students through this incredibly stressful time. It's stressful learning to do physics without a pandemic. You all know that, whether it comes from the difficulty of the material or the challenge the intellectual challenge that it poses to us, or the workload that I guess we faculty are responsible for, or whether it comes to the psychological impact of being away from each other for so long. And our student services were critical in helping our student community through that process. In saying that, there were two new additions that I'm excited to introduce to you. The first one is Anna Hilke, who I'll let introduce herself.
Hello, everyone. My name is Anna Hilke, and I'm one of the undergraduate major advisors in the department. I work primarily with students with last names A through L, and have had the pleasure of being part of the student services team since starting last October. I look forward to seeing you all on campus and on Zoom, and having a great semester ahead.
Our other addition was Christian Natividad in student services, who is a graduate advisor.
Hi, my name is Christian Natividad. I'm your newest staff graduate advisor. I work closely with Joel Miles and the rest of the student services team. I'm so happy to be here, so happy to join you for this new academic year. Go Bears!
Okay, so there are two newest additions to student services, and they've been an awesome contribution to the team, really augmenting a fantastic team that we already had. So I'm very excited to be working with them now. Okay, also our faculty and our students stepped up too. We had to transfer all of our courses online pretty much overnight. And in addition to changing our instructional practices, we also had to change the way we run our groups in our research, our meetings, our conferences. All of those things changed the way we interact together and as physicists. So our classroom started to look a lot like this. And then our student groups also got together themselves to also try and maintain the student experience over this very, very difficult time. So again, really emphasize, and of course there were some fun times too. Here's a picture from my own group. We decided to do like an online bake-off of ninja bread men. So there were some fun times, but it was only really possible because of those three key components of our community come together: our staff, our faculty, our students, really working together to keep us together. There were some other bright things that came out. It was a traumatic year for other reasons. All of the social justice protests that you saw, the contentious election, for example, but from that came some positive things too. In particular, it made us think about ourselves as a community, about how we create a more diverse, equitable, and inclusive community within our own corridors. It made us assess how we were, where we were failing, where we were succeeding, and how we can do better as we grow as a community. And last year, I asked these questions. Why does physics continue to struggle with diversity? Why do some students feel excluded in our corridors? Why does anyone feel like an imposter when they're here? What can we do about it? And finally, what can we do about it within the new reality of the pandemic or post-pandemic, or whatever stage you might want to describe the current, the status quo? And these 4 questions haven't changed because they don't change very quickly. We don't answer them overnight. It's an evolving process that we try and address as a community. But today I want to tell you a few things that we did manage to achieve over the last year that I'm very proud of. But again, just to emphasize the same point, it took the 3 communities coming together to make it possible. Okay. One of the first things that we did, spearheaded by our new Director of Administration, Roya Ferrazares. Roya, do you want to stand up and say hello? You don't have to say anything. She was muted, I'm afraid. Okay, so we had regular meetings once a month where we discussed issues of social justice, racial justice, and other challenges that we have as a community and how we might address them. And particularly our students and our postdocs, our staff and our faculty came together regularly to address these questions, not only to hear each other, but also to talk about what kinds of solutions we might have in the future. And so we came up with a few action points that I want to tell you about today. One of them was to develop a set of community principles. This is essentially a kernel of, or a nucleus of which we grow a culture in our physics community, in our physics department, that addresses really how we treat each other as a community. And we had 5 main principles that we came up with: that we value every person, we are respectful, we learn together, we speak up, and we strive to be transparent. So these are things, they're aspirational. They're aspirations of what we want to do as a community. And the idea is that we want to bring each other together as part of these aspirations, bring a community together that shares these aspirations. So that was the first thing. And now you can see our community principles posted on our website. And we will continue to advertise this and propagate this to make it a central part of the culture of a physics department. The second key part that came up is that we work closely with the Assistant Dean, Dr. Colette Pat, who drives a lot of the diversity and equity efforts in the Mathematical and Physical Sciences division. So not just our department, but also astronomy, mathematics, EPS, Earth and Planetary Sciences. And some of Dr. Pat's research actually asked the question, what kinds of cultures in a lab or in a classroom actually can affect the diversity? In other words, how people feel included in a community. So, and one of the things that came out of that research was about clearly articulated expectations, the role of ambiguity in courses or in lab work or in PhD programs. That role of ambiguity was really affecting how different students felt included or excluded from a program. And so working together with Dr. Pat, she addressed the faculty at a big retreat where we talked about this kind of question. And we decided that it was important to have a well-articulated PhD program as a first step to try and see how this would affect our community. So as of this year, we have put together a graduate student guide, which will be available to all the new graduate students, so actually all of the graduate students, also posted on our website, with some clearly articulated milestones or expectations, things that will help explain where you should be at different stages in your PhD. And so we, as a faculty, we came up with a number of ideas, but also we incorporated student feedback in this. So we had a town hall about exactly these kinds of what these milestones should include, postdocs as well. And with that feedback, we came up with this set of milestones. And this set of milestones is supposed to achieve a few things. First of all, it's supposed to clearly lay out what your expectations of yourself should be. It's an approximation of what a PhD should look like, not exact set of deadlines exactly. And of course, we haven't incorporated the effects of a global pandemic in the structure. So, but in particular, we introduced a few important things. Apart from just having a better articulated set of milestones, we also incorporated more ways to communicate. So we included a short qual proposal, for example. So students would have an opportunity to learn how to write about science. We also incorporated a poster presentation, so we could have better oral presentations experience amongst our students. And then finally, we also included the possibility of a subgroup talk towards the end of one's PhD. We really get to address the people that were your mentors, but are now going to be your peers. So with those increased opportunities of connections between faculty and students, and also better articulated structure to what a PhD should look like, we felt that this was a first step to addressing this question that Dr. Pat researched. Okay. The other key program that I'm very proud of is the Pi Squared Student Fellowship Program. So we started an undergraduate fellowship program to try and engage more undergraduates in research. So again, this is trying to incorporate more connections between those three aspects, particularly between the students and the faculty, by bringing more students into having a research experience. So we created some funded paid research opportunities for undergraduates over the summer, where we had three main components. One, connecting mentors to mentees, like I mentioned, students to faculty, and also undergraduates to their graduate or postdoc mentors. Rewarding not just scholarship, which is of course important, but also leadership. We wanted to reward students that didn't just want to be great physicists, but they wanted to be great contributors to affecting our community. And then finally, creating a cohort of young physicists. This isn't just a group that sits in their own research group, but is part of a community of scholars that will not just be here this year, but also be here next year, and will hopefully grow as the years go by. So the idea is really to try and create lasting connections between our student community, our faculty, our staff, that really cross the boundaries between our research missions and our instructional mission. So with saying that, just let me emphasize that there really was the three components coming together. We had a committee of students and postdocs, some of whom are here. I know Andres, Franco Valente, do you want to say hi? And I'm going to embarrass you too, Charles at the back, who was part of this committee. I'm not sure if Louis Guillaume is here, or Vikram, or Hannah Weaver. No, it's okay. But also they joined forces. So they were basically the selection committee that decided on who the scholars should be. Then we also had Feng Wang and Eric Bedsig, who ran the program. And then finally partnering with our staff. So Elizabeth Nakahama just here. Do you want to say hi to everybody? Also muted. Who was the program manager for the Pi Squared Fellows, and also Rachel Schaefer, who actually helped us with the fundraising to engage donors with this process, so we could keep, not only have this program run last summer, but also continue it for summers to come. And I just have a short video that I want to show you to really express how successful it was.
Learning is one of my favorite things to do, and there are a lot of opportunities in physics. So I worked with Wendy Wan, my mentee. We were basically growing an alloy series, like with different elements and like examining their superconducting properties. I think it's really important that there is like a funding source, especially over the summer, because it's the most important thing for like making an undergrad feel like they belong in the lab and that, you know, they're valued.
I work with Nicola. He not only taught me knowledge, but also taught me how to deal with problems when I encounter them. I also learned about other people's research, and we also gave each other course advices. So I do think the cohort is a very nice way for us to bond with each other. The summer ends, but the research never ends. So going forward, I plan to continue doing this project, make it a foundation of my senior thesis, and potentially publish it in a scientific journal. I might apply it to a graduate school and do more research with more fantastic people.
In my physics class in high school, we had this experiment we did where we had to predict where like this spring gun was going to shoot a ball. I just thought it was crazy to see like all of the math we've been learning and all of these things that are more abstract sort of come out to be making predictions in the real world. Our project, we're working on maybe the next generation of magnetic random access memory. I mean, working with Gerardo has been very, very important to the project.
I wasn't the best high school student, nor did I want to go to school or even college. And then I was taking some math classes that I found success in, and then I took physics at the same time. And then seeing that kind of parallel between the mathematics and the physics, and then how also the physics can take the mathematics that I was learning and then describe pretty cool stuff with it. Giant, huge help from Shannon, because she was my mentor, and I knew basically nothing about what was going on, and slowly but surely Shannon was able to like guide me and like answer some questions, and then, you know, lead me to the right places to be able to learn more and do the project. One thing that I'm excited to take forward from this program is a lot of like the skills that I gained in doing like research and investigations and carrying out experiments, and then also like seeing qualities of like Shannon's mentorship that I think are probably good, that I will probably like start to think about if I ever have a position like that.
My mentoring experience was awesome. I mean, it was really my first time really mentoring somebody, and so these initial explorations are really key for me to pick up all of the details that I kind of missed as a chemist. The project that we worked on this summer was looking at atomic spectroscopy of ruthenium. I worked with Lely Tran.
I was able to firsthand like ask questions and see what it really is like to do research and be a researcher. It was really, really important, and I would highly recommend anyone who's considering physics to have research experience, because it gives you an idea of what you'd be doing in a career.
I am so excited about that program, and there's just going to be more of those kinds of experiences for undergraduates and graduates as we go forward. So I really appreciate how much effort they put into it. Okay, so what next? Okay, so emphasize the same thing again. So students and postdocs, faculty and staff coming together as a way of really advancing our mission as a community to be more inclusive, more diverse, more equitable, and really bringing better experiences and enabling our mission as physicists. Okay. So all of us have a role to play in helping each other grow as physicists, and I think that's what those achievements that I just showed really illustrate. Okay, so now we're at a stage where I want to welcome the newest members of our community. Specifically, we have a large cohort of new graduate students who have joined us this year, and you have a great year to look forward to. We also have a large number of visitors and postdocs this year who have joined us, some earlier in the pandemic, and some of them just joined us this semester. But together, these are going to be the new group that are joining what I feel is the best physics community in the world. Okay, we also have a number of new faculty. Eric Ma, who will be joining us this semester, Raffaele Margutti from astrophysics, who joined earlier in the summer, and then Ben Safdie, a particle theorist, who is joining us this semester as well. Now I will let them introduce themselves.
Hello, I'm Eric Ma. I am really excited to move across the bay to join UC Berkeley Physics and EECS. I am an instrumentalist, and my research lies at the interface between photonics and quantum materials. I look forward to meeting all of you, and if you might be interested in building a state-of-the-art optoelectronics lab from scratch, come talk to me.
Hi, I'm Rafaela Margutti. I go by Raf in the United States. I joined Berkeley in July. I study transients, and among them, I'm very excited about those that are produced by neutron star mergers. And I'm really looking forward to meeting you all in person and chatting with you all and work together.
Hello everyone, my name is Ben Safdie and I'm new to the department this semester. I'm a particle theorist, so my main focus is on dark matter. Dark matter is most of the matter out there in our universe, but we have absolutely no idea what it is at a microscopic level. And my research focuses on the very simple question of, what is this stuff? So it's really great to be here in Berkeley, and I can't wait to get to know all of you.
Okay, so we've had, as always, a very successful year of recognition for our students, our staff, and our faculty. And I want to give you a couple of examples this year. So a couple of highlights. Trevor Grand Prix won the 2021 Schmidt Science Fellow. Trevor, are you here? No, okay. And also Kevin Langhoff and Benjamin Concepcion won the Extraordinary Teaching Extraordinary Times Award in 2021. Kevin or Benjamin, are you here? Okay. So we're really proud of our students doing really so well with getting recognition locally, but also internationally. Our staff have got a lion's share of spot awards from around campus because they just did such an extraordinary job, usually, but also particularly during the pandemic. And you can see all of the staff that got spot awards this year. And then finally, our faculty have racked up their own set of awards. I guess it looks a little bit ridiculous with that font size. So let me try and expand that on a bigger slide. So again, as always, a good half of our faculty have won some of the most prestigious awards for international recognition for physics achievement. And it's hard to pull out any one particular award because they're all so fantastic. But perhaps one notable achievement is, of course, that we got a Nobel Prize in 2020, Reinhard Genzel, who shared it with Andrea Ghez and Roger Penrose. And Andrea Ghez and Reinhard Genzel are, of course, both from University of California. Andrea Ghez is UCLA. Reinhard Genzel is emeritus at Berkeley. And of course, this was perhaps the most notable prize that we got in 2020 for the discovery that black hole formation is a robust prediction of the general theory of relativity. Okay. All right. And of course, we're #1. Who saw this last week in Forbes magazine? Great. That's right, we're #1. That's right. So we're excited to be #1. It was no mystery to us, but of course, it's nice to actually be recognized for it. But particularly what was notable about the article, I don't know how many of you read it, but in addition to having excellent scholarship at Berkeley, we also have a mission that serves a huge fraction of the public, which most of the private simply don't have. And they noted that as part of the assessment of what really makes us #1. In other words, the mission is what makes us special. Okay. So for those of you just joining us, joining Berkeley, this is a really exciting time to be doing physics. And these are my last few slides, and I think I'm good on time. So if you go to our website, broadly you'll see our physics fields categorized in 5 main groups. So astrophysics, AMO, biophysics, condensed matter, nuclear, particle, plasma, and nonlinear physics. But I would say as physics is evolving, particularly physics here at Berkeley, in many ways, these categorizations don't really make quite as much sense. And the reason for that is that there's a significant overlap between different kinds of fields. There's not only cross-hybridization, but also a direct overlap between different kinds of fields. It's not just ideas that we're exchanging, but actually techniques and intellectual capital. So what's really exciting about what's happening right now is that physics as a field is really evolving from these simple categorizations into much broader cross-disciplinary area. Let me give you an example. Many of you might have heard of the Hawking paradox. Essentially, the question, what is the fate of quantum information as a black hole evaporates? It's called the Hawking paradox because Stephen Hawking posed this question. And the paradox itself is really, is quantum information conserved, or does it evaporate into some incoherent radiation? Now, this is the kind of question that string theorists and high energy physicists often think about. This is where the holographic principle in many ways had its origins. So people like Raphael Bousso would have worked on a problem like this. Recently, we hired Jeff Pennington, who really comes more from the quantum information field, because the answer to this question really crossed over to a field which is more, which is closer to really AMO, condensed matter, if in quantum information sciences, where really this answer kind of came. And as it turns out, right now, we are one of the departments that is at the center of quantum information efforts around the globe, particularly led by our faculty like Irfan Siddiqui, who's not here in this room, but Dan Stamperkern, who is here. Dan, do you want to say hi? Really leading the effort in the quantum information sciences. So in other words, it's a place where quantum gravity, normally the realm of high energy physicists and theorists, to quantum information, arguably the realm of condensed matter physicists or AMO physicists or even quantum chemists. So that kind of interaction where one field has really been able to help answer the deepest questions in another field is not just a singular phenomenon. This is something that you're going to see over and over again as we evolve as a community. I've got other examples, but I could carry on. So for example, we have a very strong biophysics effort, but some of the biggest biophysics questions are really in systems that are out of equilibrium. What happens when you have complex systems that are strongly interacting but they haven't reached the equilibrium state? How do you answer the complexity of that question? One of the ways we've started to answer the complexity of those questions and the statistical mechanics of those kinds of systems is, of course, with data science and machine learning, artificial intelligence, where we've employed the advanced techniques that are developed by data scientists and now also developed by physicists, people like Mike DeVries or Uro Seljak here in our own department, who really thought about how to use those kinds of advanced techniques to answer big complex questions of the statistical mechanics of those kinds of systems. And of course, when we're talking about non-equilibrium systems, we only need to look at, we can also look try and understand questions of strongly interacting systems at the center of a neutron star or astrophysical nuclear reactions. Systems where not only strongly interacting, but clearly out of equilibrium, but can be advanced by techniques just developed in other fields. And now that we're talking about correlated systems and things out of equilibrium, that's actually my own favorite research area, which is condensed matter, where we really try and study what happens at the boundary of a phase transition, or particularly phase transitions at zero temperature, where things are now not only have interesting statistical behaviors or emergent symmetries coming from their statistical scaling, but also have exotic physics coming from quantum fluctuations. That kind of non-equilibrium physics relates to how we understand phase transitions in all kinds of systems, not just the solid state systems, but also phase transitions on cosmological scales. Importantly, those kinds of things not only answer fundamental questions, but sometimes they actually have applications. For example, there's a big field growing in trying to make ultra-sensitive sensors. Why would you want ultra-sensitive sensors? So for example, the kinds of things that some of our own community work on here, making ultra-sensitive magnetometers out of NV sensors like Norm Yao, to really take detection to its absolute physical limits. And that's the kind of thing that, for example, people in the dark matter field are interested in. Because now we need to find the kinds of sensors that would be useful for detecting the most obscure matter in the universe. And right now, a growing field, in fact, I'm going to be giving a talk about this in 2 days' time, apparently. So I have this evening to prepare, where we are trying to answer that exact question. Are there low energy excitations and dark matter excitations that we can detect using ultra-sensitive sensors developed in the condensed matter field? So physics really is no longer simply categorized into the small compartments that perhaps you're used to when you enter graduate school. We now really are in a truly interdisciplinary era where we are harnessing techniques developed in everything from soft condensed matter to computer science to quantum chemistry to string theory and other kinds of fundamental physics, where we try and leverage each other's techniques and understanding to understand these complex systems. So I think it's a very exciting time to be a physicist, particularly right here. I want to highlight 3 major centers which kicked off last year, particularly Wick Haxton's N3 AS Center. Wick, do you want to say hi? And the Quantum Leap Challenge Institute, again, led by Dan Stamperkin, he's already said hello, and the Quantum Systems Accelerator, led by Irfan Siddiqui. Together, each of these, put together, these are basically $200 million worth of federal investment into the quantum sciences right here in Berkeley. So this tells you that it's not only me that sees us at the center of this burgeoning field, but actually domestically, we're a national effort based right here. Okay, speaking of how we're going to grow in the future, we have 4 main searches next year. And what I've got here in the slide are the search chairs. So Liang Dai, one of our newest faculty, will be leading the search in gravity waves experiment. Mike Zalatel, Mike, I think I saw you at the back. Do you want to say hi? Will be leading the search in fundamental symmetries experiment. Carlos Bustamante, which I didn't see here, will be leading our search in soft condensed matter. And Yasunori Nomura, Yasunori, are you here? No, will be leading our search in nuclear astrophysics theory. So we're very excited that we're hopefully by the end of this year, we'll actually be welcoming 4 new faculty to our corridors. In addition to that, there are more efforts to engage our students from across different areas, again, to bring more undergraduates and graduate students and faculty and staff together in our effort to create a better community. And it turns out that there are a couple of parallel efforts led by the Mathematical and Physical Sciences division that are very similar to the Pi Squared effort. Pi Squared I've already told you about, that was specifically departmental physics department effort. But the other places were sort of lagging behind, following our lead, let me put it that way. So for example, we recently teamed up with astronomy and led by Eugene Chang and Feng Wang, we won a Berkeley Discovery Grant where we can fund what we call physics and astronomy scholars. These will create a community of undergraduate mentors who will be involved in nucleating sub-communities in different areas of our department, whether that's focusing on something technical like learning how to build experiments, or learning how to, or tutoring, learning how to be a better conceptual understanding of what's going on in their lectures, or even just how to become better mentors, better leaders in our community. So these are the kinds of, so that program is going to kick off this year, and I think applications are already open, and we're looking for the physics and astronomy scholars as we speak. And then finally, the third program, which has just started, funded by the Moore Foundation, MPS Scholars, was another undergraduate research program, funded undergraduate research program that was kicked off by the Division of Mathematical and Physical Sciences. And that should be coming online later this year or early next year. So again, there'll be lots more opportunities for undergraduates to start engaging in our research community. So I think it's exciting times. Let me give you one penultimate slide. In addition to those kinds of efforts, which you're going to see this year, we are thinking about how to do more things for our community. Right now, as an extension of our Pi² effort, we're going to try and make more interactive maker spaces, tinkering rooms. So you'll be seeing a lot of projects where students will be able to engage independently and creatively to build their own equipment or build their own sensors or build their own experiments, or just to play in the lab as independent scientists. We'll be looking for ways to create more interactive discussion spaces, things that are really important right now. Seeing the impact of places like the reading room or the particle theory interaction room or the Marvin-Cohen interaction area have been so central in bringing us, particularly our research community together and our undergraduate community together. We want to create more of those opportunities for people to discuss, debate, and brainstorm. And then finally, we want to look for more ways to support a more diverse and equitable community by creating more graduate and postdoctoral opportunities, particularly focused on leadership and scholarship. And I just want to point out one final thing here, where thanks to the leadership of Bob and Mary Catherine Bergeneau. Bob, may I embarrass you by saying hello to everybody? He established an endowed Graduate Student Equity and Inclusion Fund, which we'll be able to use to really help the department's efforts in DEI. So we're excited to kick that off. It's particularly, there was a large donation by Heising Simons, but also faculty contributed to it, like Barbara Yatzak, for example, and many others made significant contributions to really build this DEI fund so we can do something real with it as we go forward. Okay. So, ending on this slide, bringing together our three most important tools in our community to really try and fulfill our mission as a department, which is, as I see it now, to help you fulfill your mission as individual physicists. Okay, so have a great year and thank you very much. I'm happy to take questions right now. We also have some questions online. For those questions that we can't get through, we'll put them together and send out answers to after the talk. So are there any questions right now for me from the audience? Yes. Great question. Great question. So we do have some great efforts in this area that are already established. In fact, do you know Andres right there? So I hate to put you on the spot, Andres, but I know you've actually already put a lot of effort into this. If you could say a couple of words about the PGS, your effort in the tutoring, and yeah. Just, so last year, yeah. The primary focus was very often just very yeah, one program. So I want to commend Andres for this effort, because this was, as far as I know, is like really driven by you and has just been extremely successful. And you know, as a department, we want to support those kinds of efforts. we've thought a lot about this because there are, I guess, arguably other kinds of barriers to kind of making like real impact in a theory group, particularly like the need to kind of get familiar with very complex concepts before you can really start to push the boundaries of knowledge. But I think one thing that was, so I do think we want to create more opportunities for those kinds of engagements, especially like computational projects, which might have a different barrier to entry where people can still contribute. Because I think one thing that's beautiful about science in general is that you can be at any level and still contribute, right? So I think the first effort is really to try and create those kinds of opportunities, demonstrate the success, and then and because of that success, try and engage more faculty to take on those students. So what we're focused on is really creating like a sustainable model, like of the undergraduate research fellowships, where we can really maintain those kinds of efforts and just demonstrate the success and hopefully encourage more people to do it. But I think there's also something to be said, and this is a conversation we can have outside, I suppose, but that when you're an undergraduate, you're really neither a theorist nor an experimentalist. We're all learning to be physicists, and we're learning what role we have to play in physics. In principle, like we're mostly theorists because we're trying to learn all of these concepts when we're undergraduates. And then we start to get a taste of what it's like in experiment in the lab, and then the more advanced labs and so on. But when it comes to pushing the boundaries of knowledge, you can still be you can still make contributions that are in an experimental lab, but they're still mostly theoretical, and vice versa. So I think there are lots of opportunities. It's just a matter of I think at the undergraduate level, it's not always useful to distinguish, I want to be a theorist versus I want to be an experimentalist. At this stage, we just want to be physicists, and both theory and experiment are important to understand to become a physicist. Any questions from online? What's that? Oh, yeah, sure. Yeah. Yeah. Right. Absolutely. It's a great question. So I think if I could summarize the question in one line for the people that couldn't hear you, there are a few components to it, but the main part of the question is, can we look at cluster hiring as a way of, can we look at better practices for hiring as a way of increasing diversity at those levels in our faculty? But in particular, can we look at cluster hiring? Is that a fair summary? So let me address what I see as the first part of the question. So can we have better hiring practices? We have, over the last few years, tried to take on the research that has been done in these areas and try and implement them in our hiring procedures. So examples are better outreach. So outreach to broader communities and actually, so getting the word out basically, so we have as broad as community as possible actually applying. The second part is encouraging more people to apply. So that's another big factor in actually in the kinds of candidates that one gets. It's not just a simple, hiring at a faculty level. There's so few people qualified to actually, teach you quantum field theory, for example, that you really need to reach out and find the right people that can actually do that kind of job. So better outreach is an essential component. So we're trying to do that. The second part is making explicit in our hiring ads, like what we're looking for. People making explicit the kinds of people that would fulfill, that would work well here at Berkeley. So namely people that believe in our mission as a community. And that includes, of course, our mission for more diversity, equity, and inclusion. And so by putting that up front, you already send a message of the kinds of candidates that would succeed in a faculty search. And there are a few other things along the similar lines. But the one big one that you just mentioned, which was cluster hiring, also turns out to be one of the most difficult ones to try and implement. And the reason for that is the following. We've got 4 searches, but they're all in different areas. Cluster hiring really only works if you have 4 searches in one area. And for that to happen, we could put in a request for that, but it would have to be approved by the campus. And generally, this year is special for 2 reasons. One of those 4 faculty positions is actually was a surprise to us. It was an endowed position, so we didn't expect one of them. And then the other 3 searches were really to build parts of the department that we thought we needed more needed building in. So, and those are those 3 areas. The other 3 areas: nuclear astrophysics, soft condensed matter, and the fundamental symmetries experiment. But rarely would, so the first question that we get from the campus when we put in a request is, why do you need people in this area? And that's just if we ask for 1 position, and then we have to justify it. If you ask for 4 positions in one area, or even 3 positions in one area, then it becomes like orders of magnitude more difficult to justify to the campus that we need that many people all at once in one single area. And the other part is that, and part of that is the fact that the number of positions that you have in a faculty, a teaching faculty, is generally finite. We have what we call a floor, right? Which is not a ceiling, as they say, but it pretty much is a ceiling. What that means is that we have, 43, 44 positions, teaching positions for faculty, FTEs. And we can't be too much above that in terms of who we're allowed to hire, who campus will basically pay for, because the salary comes from campus. So that's the problem. You might have like 4 or a few retirements in one area, 4 retirements across the department, but they'll really be in one area. So it's really hard to justify a cluster hire to campus. So that's the challenge with cluster hiring. I agree. I think the data does show that you get more diverse hires that way. You can broaden it by, but the reality is that we haven't been as supported as I would have liked at higher levels, and you can kind of understand why. Like there are just a limited number of resources. So we do the best we can with everything else. And we're hoping that that will lead to better hiring. I'm sure that was not as satisfactory an answer as you might like, but it is a problem that is really, really tough to solve. Okay, well, thank you very much.